Okay, in this lecture we're going to cover our section 3.6 material on variation of parameters, which is another method for solving non-homogeneous second-order linear equations. So here let us consider a non-homogeneous second-order linear equation where the coefficient functions p, q, and g are continuous. And let us suppose that y1 of t and y2 of t are a fundamental set of solutions for the corresponding homogeneous equation, so that the general solution of our homogeneous equation, the homogeneous solution, would be of the form c1y1 plus c2y2, where c1 and c2 are arbitrary constants. Now, in order to find a particular solution for the non-homogeneous equation, let us consider replacing the constants c1 and c2 in the homogeneous solution by functions of t. That is, let us consider a particular solution of the form y sub p of t is equal to u1 y1, where u1 is some function of t, plus u2 y2, where u2 is a function of t. And then we need to try to determine what are the functions u1 and u2 that would make this a solution of the non-homogeneous equation. So to determine what these functions u1 and u2 are defined as to be a solution of the non-homogeneous equation, we need to find our first two derivatives of this particular solution so that we can substitute into our non-homogeneous equation. So let's start by finding our first derivative of this particular solution, yp prime. So using the product rule, we would have u1 prime y1 plus u1 y1 prime plus u2 prime times y2 plus u2 y2 prime. And before I find my second derivative, I'm going to make a simplifying assumption so that when I take my second derivative, I don't have any terms involving the second derivatives of u1 and u2. So let me say here for simplicity, let us force the sum of the terms involving the derivatives of u1 and u2, that is u1 prime y1 plus u2 prime y2, let us force the sum of those terms to be 0. And again, we're doing this so that when we find our second derivative of the particular solution, we will not have terms involving the second derivative of u1 and u2. Now, I'm going to reference this equation a little bit later, so let me number this. This will be equation 5. And so if the sum of these terms is 0, then our first derivative, yp prime, simplifies to u1 y1 prime plus u2 y2 prime. So looking at our second derivative, yp double prime, we would have, by the product rule, u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. So let's now substitute this particular solution and its derivatives into our non-homogeneous equation. So here I'll say substituting into the non-homogeneous differential equation. Let's see what we have. So we would be looking at the second derivative, which we just found, as u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime plus p of t times my first derivative, which simplified to u1 y1 prime plus u2 y2 prime, and then plus q of t times the particular solution, which was of the form u1 y1 plus u2 y2. So if I expand and group like terms together based on the order of the derivative of u1 and u2, let's see what we have. Now, the only term that I have involving the derivative of u1 is my first term, u1 prime y1 prime. And then let me group all of my u1 terms together. So let's look at these. All of the terms involving u1, I can group together. And if I factor out a u1, I am left with y1 double prime plus p of t times y1 prime plus q of t times y1. And then grouping my u2 terms together, well, the only term involving the derivative of u2 is u2 y2 prime. And then if I group together all of the u2 terms, and I factor out a u2, I am left with y2 double prime plus p of t times y2 prime plus q of t times y2. And so these two terms in brackets, or these two expressions in brackets, are exactly our differential equation with y1 and y2 substituted in. But we were told that y1 and y2 were a fundamental set of solutions for the homogeneous equation. That is, they make our differential equation equal to 0. So each of these terms in brackets is equal to 0, and therefore we are left with u1 prime y1 prime plus u2 prime y2 prime. And this has to equal g of t, or we want it to equal g of t for this particular solution to be a solution of the non-homogeneous equation. So this equation that we end up with, let me call equation 6. And so what we now have, looking at equation 5 and equation 6, is a system of linear equations involving the derivatives of u1 and u2. So let's take a look at this system. Let me copy my equations down here. We have u1 prime times y1 plus u2 prime times y2 is equal to 0 from equation 5. And from equation 6, we have y1 prime times u1 prime plus y2 prime times u2 prime has to equal g of t. So to solve this system of equations, there's a number of ways we could do it. I'm going to apply Cramer's rule, a result from linear algebra, which says that the first unknown variable, here u1 prime, could be found by taking the determinant of the 2 by 2 matrix, where the coefficients for u1 prime are replaced by the functions on the right-hand sides of my system, that is 0 and g of t, and the coefficients for u2 remain the same, y2 and y2 prime. And then we would divide by the determinant of the 2 by 2 matrix of coefficients for my system. So from the first equation, our coefficients for u1 prime and u2 prime were y1 and y2. And from the second equation, our coefficients were y1 prime and y2 prime. And similarly for u2 prime, we would take the determinant of the 2 by 2 matrix where the coefficients for u1 remain the same, and the coefficients for u2 prime are replaced with the functions on the right-hand side of my system, 0 and g of t. And we divide by the determinant of the 2 by 2 matrix where we have the coefficients for our system. So this gives us u1 prime is equal to, taking the determinant in my numerator, I have 0 minus the product of y2 and g of t. And then we are dividing by the determinant of a 2 by 2 matrix where the first row is y1, y2, and our second row is the derivatives, y1 prime and y2 prime, which we recognize as being the definition of the Wronskian of y1 and y2. In solving for u2 prime, the determinant for our numerator gives us y1 times g of t minus 0. And we're dividing by the same determinant for our denominator, which is the Wronskian of y1 and y2. So now that we have the derivatives of u1 and u2 as functions of t, we can solve for u1 and u2 by integrating. So it follows that u1 is the antiderivative of the expression that we just found for u1 prime, and u2 would be the antiderivative of the expression that we just found for u2 prime. So what we have just established is the following result. This is theorem 3.6.1 from your textbook, which is illustrating a method known as the method of variation of parameters. And it says the following: if the functions p, q, and g are continuous on some open interval I, and if the functions y1 and y2 form a fundamental set of solutions for the homogeneous equation corresponding to the non-homogeneous equation we're considering, then a particular solution would be given by yp of t, and it's equal to the product of u1 times y1 plus u2 times y2. These expressions that we have here are exactly u1 and u2. And therefore, our general solution for this non-homogeneous equation would be the sum of our homogeneous solution and this particular solution. So some things to note here. I will mention first that these formulas for u1 and u2 that we have derived are useful to have memorized for the purposes of your homework or exams. And the formulas for u1 and u2 that we derived involve the function g of t, and this g of t function was the function on the right-hand side of our equation after it has been written in standard form. So it is important to note that this equation is expressed in standard form. So in order to use these formulas that involve g of t, to make sure we're working with the correct g of t function, we need to make sure our differential equation is in standard form. Now, one other thing to note is that a major advantage of this method of variation of parameters is that we can solve a non-homogeneous equation with an arbitrary forcing function g of t, as long as it's continuous. That was our only restriction here. So this method is a little more powerful than the method of undetermined coefficients, because undetermined coefficients only worked in the case that g of t was a polynomial, an exponential, or a sine-cosine function, or products of those types of functions. This method of variation of parameters, all we need is continuity of g of t, so we have a more powerful method for solving these non-homogeneous equations with this technique. So let us consider some examples to make use of this new method. In this example, we are asked to find the general solution of this differential equation, and we see that it is second order and linear with constant coefficients, and it is non-homogeneous because our g of t function on the right-hand side is non-zero. And here we see that this g of t function is not a polynomial, an exponential, or a sine or cosine function. It is a cosecant function. So for this type of g of t function, we could not use the method of undetermined coefficients. We need to use this new method known as variation of parameters. Now, our first step in solving any non-homogeneous equation is to first solve the corresponding homogeneous equation. So let us start there. If we consider our homogeneous equation, y double prime plus 4y equals 0, then we could solve by looking for a solution of the form y equals e to the rt power, so that r would be a root of the characteristic equation, r squared plus 4 is equal to 0. And so it follows that r would be plus or minus 2i. So we're working with the case of complex conjugate roots of the characteristic equation, which means that the homogeneous solution would be of the form c1 times cosine of 2t plus c2 times sine of 2t. Now, to find our particular solution using this method of variation of parameters, we're going to use the formulas that we derived for u1 and u2, and both of those formulas involve the Wronskian of y1 and y2, which were a fundamental set of solutions for our homogeneous equation. So let's give these functions that make up the homogeneous solution a name. Let me say that y1 of t is the cosine of 2t function, and y2 of t is the sine of 2t function. So that my Wronskian of y1 and y2 would be the determinant of the matrix where my first row would be cosine of 2t and sine of 2t. And my second row, the derivatives, would be negative 2 cosine of 2t, negative 2 sine of 2t, and 2 cosine of 2t. So taking my determinant, I would have 2 times cosine squared t plus 2 sine squared t. And since the sum of sine and cosine squared is 1, we're left with 2 times 1. So once we have this Wronskian, we're ready to calculate the u1 and u2 functions. So here, u1 of t was defined as the negative integral of y2, which is sine of 2t, times g of t, which was 3 cosecant of 2t, over the Wronskian, which we just found to be 2 dt. So here we could pull out a factor of 3/2 in front of my integral, and I'm left with the integral of sine 2t times cosecant 2t. Now we know that cosecant is just 1 over sine, so when I take this product, I'm left with just a 1. And so my antiderivative is then negative 3/2 t. And now let's find our u2 function. u2 is defined as the positive integral of y1, which is cosine of 2t, times g of t, which is the 3 cosecant of 2t, over the Wronskian, which we found to be 2, integrating with respect to t. So as before, I could factor out a constant of 3/2 in front of my integral, and I'm left with the product of cosine 2t and cosecant 2t. So rewriting the cosecant 2t term as 1 over sine, we are left with cosine of 2t divided by sine of 2t dt, which we can integrate by making use of a substitution. So here, to evaluate this integral, we could make use of a substitution. Let's say u is our denominator, sine of 2t, so that du would be 2 cosine of 2t dt. And making this substitution, we can rewrite our integral as 3/4 the integral of 1 over u du. So we would have 3/4 the natural log of absolute value u, which was sine of 2t, for our antiderivative. And so once we find u1 and u2, we have our particular solution. Our particular solution, y sub p of t, or capital Y of t, is given by u1, which was negative 3/2 t, times y1, which was cosine of 2t, plus u2, which was 3/4 natural log of sine 2t, times y2, which was sine of 2t. And so once we have our particular solution, our general solution is then just the sum of our homogeneous and particular solutions. So writing it out, our general solution, y of t, would be c1 times cosine of 2t plus c2 times sine of 2t plus our particular solution, which was negative 3/2 t cosine of 2t plus 3/4 the natural log of absolute value sine 2t times sine of 2t. All right. Now, a common question that students have when applying this method is regarding constants of integration. So I often get the question when I calculate u1 and u2, why did I not include a constant of integration for each of these antiderivatives? And the simplest answer to that question is that we only need one function for u1 and u2. I don't need to consider every possible function for u1 and u2. So I could choose my constant of integration in each case to be 0. Now, if you include a constant of integration for C1 or for u1 and u2, and write out your particular solution with those constants, you'll see that when you take u1 times y1, you'll end up with a c1 times y1 factor. And if you have a constant of integration for u2, when you take u2 times y2, you end up with a c2 times y2 term. But constant multiples of y1 and y2 were already part of the homogeneous solution. We don't need to include those as part of our particular solution. So in short, we do not need to consider these constants of integration when we're calculating u1 and u2. So let's look at another example. Here we're asked to find the general solution of this second-order linear non-homogeneous equation. And again, we see that our g of t function is not a polynomial, an exponential, or a sine-cosine function. So we cannot use the method of undetermined coefficients here. We're going to need to use variation of parameters. Now, our first step in solving any non-homogeneous equation is to consider the homogeneous equation. So here let us consider y double prime minus 2y prime plus y is equal to 0, which we could solve by considering solutions of the exponential form y equals e to the rt, so that r is a root of the characteristic equation, r squared minus 2r plus 1 equals 0, which factors as r minus 1 quantity squared. So we have a repeated root of positive 1, which means that our homogeneous solution would have the general form c1 e to the t plus c2 times t e to the t. And to find our particular solution, we're going to calculate u1 and u2 using the formulas we derived. And again, both of those formulas involve the Wronskian of the solutions for my homogeneous equation. So let's give these functions some names. We have y1, which I'll call e to the t, and y2 will be my t times e to the t. So the Wronskian of y1 and y2 would be the determinant of the 2 by 2 matrix, where my first row would be y1 and y2, and my second row would be the derivatives, e to the t and e to the t plus t times e to the t. So taking my determinant, I get e to the 2t. So now we're ready to calculate u1 and u2. u1 was defined as the negative integral of y2 times g of t. So taking y2 times our g of t function, we have a numerator of t times e to the t squared, or e to the 2t, over t squared plus 1. And then we're supposed to divide by the Wronskian. So dividing by e to the 2t, we see that a factor of e to the 2t will cancel. And so we are left with the negative integral of t over t squared plus 1 dt. And we can evaluate this by making a substitution. So here, if I consider a substitution of u equals t squared plus 1, then du would be 2t dt. And I can rewrite my integral as the negative integral of 1 over 2u du, which gives me a negative 1/2 times the natural log of absolute value u, which was t squared plus 1. And again, we don't have to consider a constant of integration here, since I just need one function u1 that satisfies my equation. So I could choose my constant as 0. And now calculating u2 of t would be the positive integral of y1 times g of t. So taking y1, which was e to the t, times our g of t function, we get a numerator of e to the t squared, or e to the 2t, over t squared plus 1, and then we divide by the Wronskian, which was e to the 2t. So again, we find that a factor of e to the 2t will cancel, and we are left with the integral of 1 over t squared plus 1 dt, which we know is arctangent of t. So once I have u1 and u2, I have my particular solution, which is given by u1, which was negative 1/2 natural log of t squared plus 1, times y1, which was e to the t, plus u2, which was arctangent of t, times y2, t e to the t. And so my general solution to this equation is then the sum of my homogeneous solution, C1 e to the t plus C2 t e to the t, and my particular solution, which was -1/2 natural log of t squared plus 1 e to the t plus arctangent of t times t e to the t. Now let's look at one last example. In this last example, we are considering the non-homogeneous equation shown here, which is second order linear and non-homogeneous. And here our coefficients are no longer constants, but functions of t. So here we are asked to verify that y1 and y2, these given functions, are solutions of the corresponding homogeneous differential equation, and then find a particular solution of the non-homogeneous equation. So let us first verify that y1 and y2 are solutions of the homogeneous equation. If we start with our first function, y1, which is t, then our first two derivatives, y1 prime, would be 1, and y2 double prime, y1 double prime, would be 0. And so substituting into our differential equation, we would have t squared times the second derivative, which was 0, minus t times t plus 2 times the first derivative, which was 1, plus t plus 2 times y, which was t. And so we have t times t plus 2 minus t times t plus 2, which leaves us with 0. So this is indeed a solution of the corresponding homogeneous equation. Now let's take a look at y2, which was t times e to the t. So we would have here for our first derivative by the product rule, 1 plus t times e to the t. And for my second derivative, y2 double prime, by the product rule, I would get 1 e to the t plus 1 plus t e to the t. So altogether 2 plus t e to the t. And substituting into my equation, we would have t squared times the second derivative, which was 2 plus t e to the t, minus t times t plus 2 times my first derivative, which was 1 plus t e to the t, plus t plus 2 times the original function, t e to the t. So expanding and grouping like terms, we find that we get a value of 0, and so y1 and y2 are solutions of the corresponding homogeneous equation. Now, to find our particular solution, we're going to make use of the method of variation of parameters using the formulas that we derived. But recall, to make use of those formulas, we need to make sure our equation is in standard form. So at the top here, rewriting our equation in standard form, we could divide through by t squared, and we would have y double prime minus t plus 2 over t, y prime, plus t plus 2 over t squared, y, is equal to 2t. So here, our g of t function that we're going to make use of for the variation of parameters formula would be 2t. So for that method of variation of parameters formula, we need to calculate the Wronskian of y1 and y2. So let's look at the Wronskian for y1 and y2, which are functions of t. We would have the determinant of the 2 by 2 matrix, where our first row would be y1 and y2, and our second row would be the derivatives, 1 and 1 plus t times e to the t. So taking our determinant, we get a t squared times e to the t. And now let's calculate our u1 and u2 functions. u1 is defined as the negative integral of y2 times g of t. So y2, we had t e to the t times g of t is 2t, divided by our Wronskian, t squared e to the t. And we find that a factor of e to the t will cancel, along with a factor of t squared, leaving us with the negative integral of 2 dt, which gives us negative 2t. And now to calculate u2, we have the positive integral of y1, which was t, times g of t, which is 2t, divided by our Wronskian, which was t squared e to the t. So again, we find that a factor of t squared will cancel, and we are left with the integral of 2 divided by e to the t, or 2e to the negative t dt. So we get an antiderivative of negative 2e to the negative t. So we then have a particular solution, capital Y, of the form u1, which is negative 2t, times y1, which was t, so we get a 2t squared, plus u2, which was negative 2e to the negative t, times y2, which was t e to the t. And this simplifies to negative 2t squared minus 2t. So we have found a particular solution that we were asked for, and our general solution of this equation would then be given by our homogeneous solution, which would be c1 y1 plus c2 y2, plus our particular solution, which was negative 2t squared minus 2t. And we see here that we could simplify a bit further if we combine the constant multiples of t. We get something of the form c1 minus 2 times t plus c2 t e to the t minus 2t squared. And since c1 is an arbitrary constant, c1 minus 2 is just some new arbitrary constant. So we could really write this as c1t plus c2t e to the t minus 2t squared.